Hello and welcome back to Introductory Electromancy. In this episode, we will be wrapping up our transcranial direct current stimulation device, which is already largely built. Transcranial direct current stimulation enables you to run a current through your brain and alter the way that it is operating. Different placements of the electrodes do different things. Were I to recommend you one, I would recommend this one with 2 milliamps of current for 20 minutes, 3 times a week, until you feel the effects are sufficient. Now, we have built this device after having calculated its properties, which you can see in previous episodes if you've missed them. Its actual measured output current is 1.90 milliamps, which is a little bit less than 2. The 2 milliamp safety limit is, to the best of my knowledge, a conservative one, which was arrived at in about 2010 is when this was published. 2 milliamps, durations up to 20 minutes, and electrode area of 25 to 35 square centimeters. So the electronic parts for this you can get on eBay. That is where I would recommend getting them. These are sold as TENS leads, TENS. These are sold as TENS electrodes, TENS. That's for transcutaneous electronic nerve stimulation, which is their more common usage. But these 2 millimeter pin leads can be adapted for use for transcranial direct current stimulation, and the electrodes can be adapted as well, basically by ripping off the gel and then sewing a piece of sponge over them, which will provide you electrodes that are capable of going over areas that have hair, which your head may have. I'm pretty sure you know where to get cellulose sponges, but yeah, use cellulose sponges, not foam sponges. I think they work better, to the best of my understanding. In any case, we're at the point where we add output leads to this. Now, these TENS leads are pretty squirrely to solder to. They don't have regular stranded wire in there. They have a wire that it's wrapped around some sort of polymer core. It looks like the core inside a paracord. So polyester, I guess. You can expect to see either a coil of copper foil wrapped around a core of polyester strands, or a couple of thin copper strands that are running in parallel with a polyester core. And good heavens. So it looks like these ones are the type that have copper foil wrapped around the polyester. So it might look like ordinary stranded wire, but it is not. It will be very weak, burn and melt off as you solder it, and will require strain relief. Hot glue is the easiest way to accomplish that. Otherwise, it will break very rapidly and stop working. But before attaching it to the board itself, I have had the best luck soldering it beforehand. I'm waiting for my soldering iron to warm up. If I sound a little tired, it's because I thought this would be 2, maybe 3 videos, and it has turned into more than that, but we are almost done, dear viewer. Now, if you want to use sponge electrodes instead of gel electrodes, you will need saline solution, and the recommended concentration that I received from my contact in Hong Kong in 2015 was to use 9 grams salt to 1 liter of water, which he said is near 1.5 teaspoon of salt to 500 milliliters of water. In my understanding, I'd think somewhere around isotonic saline would be the best. That is the concentration of salt that is in your squishy human body, dear viewer. However, pretty much any concentration works, from small to a saturated solution of salt. However, having a saturated solution of salt in contact with your skin for long periods may cause irritation. In any case, this has gotten to be quite the series, but the idea is you build something like this, you get a group of like-minded individuals, you and the others modify your own minds to become better than the default human you were before. Now, let me see if I can zoom in and show you what is going on here, because this is a tricky soldering job. So as the wow, I've been at this for too long today. As the polyester, or whatever material it is, core melts, the wire will tend to splay as you solder it. Unlike normal wire, see how it puffs up? And also it produces more smoke than normal. It's just difficult and poor wire to solder to, but it is necessary to be compatible with the most commonly available gel electrodes. Also, I should mention you can get sponge electrodes that are commercially made that are suitable, that take a 2mm pin. But making your own is much cheaper. And that's because gel electrodes are much cheaper. So you would take your gel electrode and then peel the gel off of it. Using gel electrodes by themselves, you can get what's called an electrode burn, and that's when the current tends to concentrate in a tiny area, and it creates like a damaged area. It kind of resembles a pimple. But if you peel the gel off of a commercial gel electrode, then you get just a carbon-backed electrode and a glob of gel, which you can use for whatever purpose. But then you sew a sponge piece to it, and that lets you get a sponge electrode that you can then saturate with your 9 grams salt to a liter of water solution. These are cellulose sponges. They seem to work better than foam sponges for this application. But you'd cut it to size and then stitch it to this electrode, and then that would be compatible with these 2mm pins, which are normally sold for TENS, transcutaneous electronic nerve stimulation. Good heavens. All right, so this is the output. You can see that, maybe you can't see. You're not allowed to see. The solder didn't fully penetrate the wire like it would normal stranded wire. This stuff is kind of a pain to work with. So I clip off the extra ball of solder part, and then this is the best condition I've been able to get it to for soldering to a printed circuit board. Now, you take your printed circuit board, and then This one is the positive output, I can see, because it is connected to one of the contacts of the switch. So that would be the red wire. And then the other one is connected to the guard safety resistor and then the collector of the transistor. So that'll be negative. So cut those to desired length. Then tin them with solder, like so. Then attach them, making sure you can see what I'm doing to the extent possible without burning myself. So a gentle tug, gentler than you would usually use, because these wires at this particular point are very weak. They're strong otherwise, but this needs an extra blob of hot glue to function as a strain relief. Maybe some super glue over the hot glue to harden it, if you want to be on the extra safe side. So now, kind of did this in the wrong order. See how the wire will pop off if you allow it to reflow, as I have just done. That is unfortunate. It means I must redo my work. But with a temperature-controlled soldering iron, you get more or less infinite redos, dear viewer, which is something I'm sure you'll be pleased to hear. Little solder to tin. Then the plus is on the top. I guess it's better for video information purposes. Okay. Minus is on the bottom. Not really happy with how that joint ended up looking. That looks more secure to me. All right, and I have connected the positive to the positive. So now these get some hot glue to strain relief them, and then we're at the point that we can attach batteries and test the output current. Oh, also I should note your resistance with gel electrodes is 5.1 kilo ohms, roughly. I have not tested it with sponge electrodes. I really should. But if you want to do more math on this circuit, you're about a 5.1 kilo ohm resistor. So that hot glue will spread the tugging and whatnot that will occur. And then we'll be ready to attach some batteries to this. And then we'll be all set. You'll be ready to start your very own brainwashing cult. Neuromodulation cooperative. So that you and your selected team of allied humans can save the world after you finish making yourself superhuman. Not significantly superhuman, but marginally superhuman, which is much less exciting, but also much less dangerous to pursue. So, someday I'm going to build my dream hot glue gun that also has a pipe that blows chilled air to speed up things like this. That is probably set enough, borrow these 9-volt batteries, and attach them. So this would be the final device that you end up with following these instructions. And nominally it provides a 2 milliamp output current. In practice, having built several dozen of these, the actual output current ranges from 1.9 milliamps to about 2.03. It may also be the meter that I'm using, which is itself not particularly accurate. All right, so the power LED turns on, and the output current, which I may as well measure with both meters since I have them available. Do not need the soldering iron on, it will only cause me problems. So question 1, does the power switch work? Yes. Great. Question 2, does it provide 2 milliamps or slightly less of output current? If it performs the same as it did on the breadboard, which it should, aside from the tiny resistance of the breadboard contacts, it should be almost identical. I should measure 1.90 milliamps. Do I measure 1.90 milliamps? Yes, 1.90, 1.91, so it would be 1.905, which is already beyond the accuracy of this meter. I think this meter is only good to 2 or 3%. 1.91. So that is what this should do if you build it. I want to check this with the other meter. And there's a safety step I want to include here. So with the other meter, I measure 1.93 milliamps. So the meters do not agree with each other, but in either case it is slightly below 2 milliamps. The target nominal output current of this design is 2 milliamps, but all the resistors are only rated to within plus or minus 5%. Now, one final step before I leave you. This is the part where we make sure the safety functions are working properly. You short the output. This particular circuit, it'll just supply 2 milliamps through the short. It doesn't even really care about being shorted, which is nice. But these two resistors on the bottom right, these are the safety limiting resistors. They correspond to these two in the schematic. Those are the ones that protect you in case the transistor fails short circuit. So you want to make sure that they have a voltage across them, because if they measure 0 volts across them, then they are shorted somehow, and that means they are not doing their job. Without these two resistors, the circuit will still measure the same output current it would with them, but they're important for safety reasons. So, given that there's 1.9 to 1.93 milliamps flowing out of this circuit, and those are 2,200 ohm resistors, let's say 1.9 milliamps, because V equals IR, I is 0.0019. In your device, ideally, it should be 0.002, 2200. So about 4.18 volts should be across each of those resistors. So call it 4.18 volts plus or minus 10% for your testing purposes. So with the device on and the output shorted, and I'm not paying attention to polarity, so some of these will measure negative. That's fine. It's the magnitude that we care about. 4.14, great, perfect. And the other resistor, 4.16, great, perfect. So they are in the circuit and they are exhibiting their protective function. The reason they measured different values even with the same meter is because these are plus or minus 5% resistors. So even with an identical current flowing through them, the different resistance values mean that they have slightly different voltages, but they shouldn't differ from the rated value by more than 5%. So I believe you're all set. You'll need this device based on this schematic, which itself is from instructions that I wrote in the past, already linked in the description. tDCS placements is a good place to look up what different placements of electrodes do. If I were to recommend one, it would be this one. The links on tDCS placements seem to be broken. I don't know why, because just searching for the text brings up the page itself, which then links to the study that the statement is based on, which I was eventually able to pull up as a PDF. And you'll want to use 9 grams of salt per 1 liter of water, which, according to my contact in Hong Kong, is about 1.5 teaspoons per 500 milliliters. Not sure why I've lost focus. It is no matter. This is just the recap section anyway. To make your own electrodes, buy TENS gel electrodes and rip off the gel, which leaves you with a carbon-backed electrode, which you can then stitch some cellulose sponge to. And those are the safety testing procedures. That is the schematic, I think. I have actually successfully communicated all of this to you